Chapter 10. It's a fun chapter. Anyhow, so yeah, here we are, Chapter 10, the last chapter of New Material in Chemistry 3101. Chapter 11 is just a review chapter. And everything that we've dealt with up to this point always involved a pair of electrons, whether it was a lone pair on an atom or a pair of electrons in a pi bond or a sigma bond. But in this chapter, we're going to talk about radicals, and radicals are unpaired electrons. So we haven't discussed those very much at all. So let's see what it says here. It says, if we break a bond, okay, there's, what do we talk about in chemistry class? Bonds, right? A lot of bonds going on. So carbon-carbon bonds, carbon-hydrogen bonds, carbon-oxygen bonds, et cetera, et cetera. Well, there's two different ways you can break a bond, as a matter of fact. One way is heterolytically, and the other way is homolytically. And you can see that heterolytic bond cleavage is shown here on the left. Heterolytic, hetero, different, right? What happens in heterolytic bond cleavage is you use a double-headed arrow, which is the arrow that we've been using the entire class, okay? Because this arrow, when you have a double-headed arrow, it represents the flow of two electrons. And so both of the electrons end up on one atom to make an anion, and the other one is left over as a cation. So that's heterolytic bond cleavage. You've seen it many times in our mechanisms. But when we talk about bond dissociation energies, and we talked about these in chapter 6, we talked about bond dissociation energies, and we use them to calculate, those to calculate the delta H for a reaction, okay? If you remember those bond dissociation energies, they came from a homolytic bond cleavage, and homolytic bond cleavage just means that everybody splits up the electrons equally. So here we have two electrons in our bond. There's no debating that. And when we draw a fishhook arrow like this, it represents the flow of one electron. And so the atom X gets one electron, the atom Y gets one electron. And when you have an unpaired electron, we call it a radical. So unpaired electron, we end up with a radical. So you see that when we look at bond dissociation energies, we're talking about homolytic bond cleavages, which result in a pair of radicals. So let's see here a little more about these fishhook arrows. So it's not just a name I made up. Okay, this is actually what we call them. We actually call them fishhook arrows. Okay, and they show the movement of just one electron. Now, again, for all of our mechanisms that we've been drawing up to this point, we always used a double barbed arrow, which showed the motion of two electrons. But now we're going to be talking about fishhook arrows in this chapter. Another time you would have seen these fishhooks was when we looked at alpha cleavage. And so we looked at alpha cleavage in mass spec. What else did we look at? We looked at McLafferty. So McLafferty rearrangement in mass spec. I'm trying to think. I think those are the main ones that we looked at that involved fishhook arrows. But I told you didn't have to know how to draw them back in chapter 14. Anyhow, so what about the molecular geometry of a radical? Right, everybody here that's hearing the sound of my voice knows that a carbocation, the carbon is sp2 hybridized, it is trigonal planar, there's no debate surrounding that. And if you have a carbanion, it's the carbon is sp3 hybridized, right? It has 3 regions of electron density, 1, 2, 3 bonds, and 1 lone pair. So that means it's sp3 hybridized. But in terms of its molecular geometry, well, remember, molecular geometry only considers the bonds, just this part here. And so it's trigonal pyramidal, and there's no debate about that either. But what if we have an unpaired electron on our carbon? So if we have a carbon radical, is that going to be trigonal planar, or is it going to be trigonal pyramidal? Like, what is it exactly? Well, let's answer that. It says radicals appear to be trigonal planar, like they're sp2 hybridized, or shallow trigonal planar that's rapidly interconverting. So we either can think of it as being flat, like trigonal planar, like this, or you can think of it as a very, very shallow pyramid. I mean, so shallow that it just inverts like nothing. Like the barrier of energy of inversion here is like practically nothing, okay? Well, I'll tell you what the answer is going to be for us as Chemistry 3101 students, okay? We are going to treat all of our carbon radicals as if they are trigonal planar, okay? So I'll put here Chemistry 3101. And for my students who are planning on taking Organic 2 at UCCS, I'll put Chemistry 3111 there as well, because in these classes, we treat our radicals as if they are trigonal planar, okay? And when is that going to be a consequence? When we look at the mechanism of something like a halogenation, okay, and we could end up forming a new chiral center, okay? That's when this is really going to be important. But in the meantime, I could just ask a question on a quiz, what is the molecular geometry of a carbon radical? And you're just going to say, well, it's trigonal planar because that's what it says in the book, okay? And that's how we treat them. All right. Who remembers carbocation stability? When we talked about carbocations, we said that a tertiary carbocation, for example, is more stable than a secondary carbocation, which is more stable than a primary carbocation, which is more stable than a methyl carbocation, right? I'm sure you all remember that because you've seen it come up so many times conceptually in this class. Well, good news is that radical stability follows the same trend as carbocation stability. You see it right here. It says radicals follow the same stability trend as carbocation. So even a radical doesn't have a formal charge, okay? If you think about, just pick the methyl radical, right? How do we determine formal charge? Well, if you use my recipe, you say 4 valence electrons minus 3 sticks minus 1 dot, which gives you 0. So a carbon radical has no formal charge. But why is it unstable? It's because it doesn't have a complete octet. Right? If you think about this carbon, it's surrounded by 1, 2, 3, 4, 5, 6, 7 electrons. So even though it's neutral, it's not surrounded by an octet, and so it wants another electron. But again, as far as stability goes, carbon radicals follow the exact same stability trend as carbocations, meaning tertiary is going to be more stable than secondary, which is more stable than primary, and methyl is not going to be very stable at all, okay? And so the reason why a tertiary carbocation is more stable than a secondary is because that R groups, even though they're not strongly electron donating, they are electron donating to some degree. So why didn't that work that time? Anyhow. All right, anyhow, so you see they are electron donating. So we have a slight dipole. It's not huge, but there's a little bit here, and that helps increase the electron density on that carbon that is electron deficient, which helps to stabilize it. So again, following the same trend as who? As a carbocation. So that's good news. So there's no really huge new rule to memorize there. But remember when we talked about carbocations, we went beyond tertiary, secondary, primary, and methyl carbocations, didn't we? We talked about things like allylic carbocations and benzylic carbocations and how they react in SN1 reactions. So if that's still in your mind, that's going to come up too. Now, if we put a number to it, okay, if we try to do some kind of quantitative analysis of radical stability, it says here that bond strength is inversely proportional to carbon radical stability. So what that means is that you could say here, more stable radical. So more stable radical means it's going to have a weaker bond. So if we take this compound here, so this is called isobutane. You can see the bond dissociation energy here for this carbon-hydrogen bond is 381 kilojoules per mole. And if you compare that to the bond dissociation energy of methane, for example, you can see that methane has a much stronger carbon-hydrogen bond. Why? Because it doesn't want to let go of it. Now, why would that be? Well, I'm sure you've got it figured out already, but it's because if I was to lose a proton here, I end up with a methyl radical, right? And here I would end up with a butyl radical like this, an isobutyl radical. Well, this is a tertiary radical and this is a methyl radical. So which one's more stable? This one is much, 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 much more stable. And so you might think, okay, well, what's the difference? 381, 397, 410, 435. Well, the difference between 381 and 437 is huge. That's a big, big difference. And so this bond is much weaker. Why? Because you end up forming a more stable radical. And so just to kind of whet your appetite as to what kind of questions are we going to ask or can I ask about radicals, one of the things that we'll do is we'll show you a molecule and ask you, which one is the weakest CH bond in the molecule. And so you have to be able to look at the molecule and say, well, if I abstracted this proton, I would end up with a primary radical, whereas if I pulled this one off, I'd end up with a tertiary radical, right? But again, going beyond that, okay, can we have a radical that's more stable than a tertiary radical? And the answer is yeah, okay? If you have something that's going to be stabilized by resonance, right? You guys know that resonance serves to stabilize a molecule or an anion or a cation. And so the same thing, we see the same thing with a radical. Okay, if we look at an allylic radical, you might just stare at this and say, well, that's not going to be stable because this carbon is only attached to one carbon. It's primary. Yeah, it is primary, but we can draw fishhook arrows and come up with a resonance. I don't know why I drew double barbed arrows. I think I need more coffee. Anyhow, you get the idea. There we go. So we can draw this resonance form over here. And again, electrons are like hyperactive children. If you give them room to move, they'll take it. And so what that does is I don't know if it does it with kids, but maybe it does, serves to stabilize them a little bit, gives them some space to move around. And so the allylic radical pattern, so if you can identify an allylic radical, right? So if we think about these carbons, you guys know that these two yellow ones, those are vinylic carbons. This one here, if I highlight it in red, that's an allylic carbon. So if you find an allylic radical like this, you can always draw the same three fishhook pattern. So we form the bond, right? If two fishhooks meet together, they form a bond. So where these two are kind of meeting together in midair, that's where the bond is being formed, and then the other electron's being put on the end. So you draw your resonance arrow, and then you'd put the double bond over here this time and put the unpaired electron here like this. So let's get some practice in drawing some resonance forms of a radical. So you can see this is a benzylic radical here. Since it's laden with these fish hooks, I'll just redraw it here. So the benzylic radical looks like this. Okay, so you have your aromatic ring, benzylic position, and there's an unpaired electron there. Well, it says the benzylic radical is even more stable than allylic. Well, why would that be? Because it's got even more resonance forms. Okay, so you can see, again, we have an allylic, right? Here's your double bond. You go one carbon away, there's your radical, right? Same thing here. You have a double bond, go one carbon away, there's your radical. So now what we're going to do is we're going to draw the result of this. So we're going to start by drawing the skeleton, which is a six-membered ring. Okay, I'm going to put the double bond in here outside of the ring because we didn't do anything with that. Then we're not touching this double bond either. So what's happening? You see where these two fish hooks are meeting together? We could say bond is being formed here. And so we're going to draw a bond here. And then you broke this bond, right? But one of the electrons went to make the new bond. And one of the other electrons is going to go over here, okay? So can we draw another resonance form? Yeah, absolutely, because here we have an unpaired electron, the double bond. So we're going to make this electron meet with this one, and then this electron is going to go over here. We're going to put in our resonance arrow. Got to use the proper arrows, right? So we're going to put our six-membered ring, which looks something like that. I didn't touch this bond. I didn't do anything to this bond, so we'll just leave it the way it is. But I formed a bond here, and now I have an unpaired electron here. Technically, these are all the resonance forms, but I'm going to draw the last one where I put the unpaired electron on the methyl group outside of the ring. Kind of running out of space here. Need some more blank space. Maybe I should buy some tickets to go see Taylor Swift. But anyhow, there we go. So we're going to move that electron up there, and we're going to draw our last resonance form, which looks like this. And there you have it. So there are the resonance forms of the benzylic radical. Give me a thumbs up if you think you could draw that after a little bit of practice. It's always the same three arrows every time, okay? Same three fish hooks over and over and over and over and over. Well, you notice that I said that a benzyl radical is even more stable than an allylic, and an allylic is even more stable than a tertiary radical. And if you want to quantify that, well, I have some numbers right here. So if we look at the carbon-hydrogen bond, that would result in a tertiary radical. You see its bond dissociation energy is 381 kilojoules per mole. But you see that this one is almost 20 kilojoules per mole weaker. And so that tells us that the allylic radical is more stable than the tertiary. Then if you go all the way down to the benzylic, whoa, it drops off even more. So benzylic carbon-hydrogen bonds are even weaker. They're even more prone to abstraction. Why? Because you end up with an even more stable radical. This is one of the things I tend to like, and I don't expect everybody to feel the way I do about organic chemistry, But this is one of the things I like about it, because to me, it seems rational. Now, is it rational to everybody? Of course not. But that's one of the things I kind of like about the subject, is it kind of goes together. So um, there we go. So now what about unstable radicals? If you remember, and don't draw this because it's a heresy. I mean, this is America. I could be arrested for this. But if you draw um, a vinylic carbocation, that is a huge no-no, okay? Same thing if you draw a vinylic carbocation. These are like, again, these are almost, I'm borderline committing a crime here or something, okay? I could be prosecuted for this. I'm kidding. But anyhow, these are so unstable, it's not even funny. And so we see the same kind of trend with vinyl protons, okay? If you were keeping track of the numbers, this was the highest number that I think we saw. Sorry, it was the methyl anyhow, which is around 435. But this is still pretty high, 410. But then you go to vinylic protons. Whoa, those skyrocket all the way up to 464 kilojoules per mole. It's a huge difference between these two numbers, okay? And so vinylic radicals, don't draw them because they aren't a thing, okay? This bond is so strong, meaning this bond here, it does not want to break. It's vinylic radicals aren't a thing, so don't draw them, okay? Very unstable. Now, here's a question that students tend to like. I don't want to use the word straightforward. Nothing is straightforward in the class, but I think that students usually figure this out pretty quickly. In A and B, all it's asking us to do is rank the radicals in order of stability. So if I just put a line here, I'll call this one A, this one B, and this one C. Out of those three, could any of you tell me which one of these would be the most stable? And it's not a trick question or anything. It's just kind of identifying. Yeah. Yeah. Thanks, Aaron. Absolutely. So this one here, we'll put here most stable. And Aaron's rationale, he doesn't even have to tell me. I know why. He's going to say it's because it's tertiary. Yep. There you go. Which one would be the least stable? Anybody? Yeah. Thanks, Aaron. It's going to be A because it's primary. Yep, so let's pencil that in here. We'll put primary, we'll put here least stable, and then C is secondary. It's somewhere in between. If I didn't mention it, and I don't think I did already, is that radicals, so radicals never undergo a rearrangement, okay? They don't undergo any kind of rearrangement. Carbocations do, there's no doubt about that, right? But radicals, if you're wondering, oh, could this rearrange to make a tertiary radical? No, it doesn't. Okay, so radicals don't rearrange. All right, and the ones on the bottom, if I call this one A, B, and C, could anybody tell me which one is the most stable out of those three? Anybody have an idea which one's the most stable out of those three? Yeah, thanks, Hannah. Yep, absolutely. Most stable is going to be B. And Hannah says the reason why is because it's tertiary. The least stable is going to be C. It's primary. So least stable is C. It's primary. And then A is secondary. It's somewhere in between the two. All right. So with that in mind, I think this is another great question where it just says, get some practice in drawing resonance structures for each of the following radicals. I just want to do the first one, and we'll save D for later on. But the first one is really great because you can, I don't know if clearly, but hopefully you can see the allylic radical. I'm just going to draw my open bracket here. You can see the allylic radical is right here, okay? See the double bond, go one carbon away. There's your unpaired electron. So that's where we're going to start with our fishhook arrows. So I'll put in my resonance arrow and let's draw some fishhooks. So we're going to make a new bond like this, and then we're going to break this one and put the electron up on this carbon at the top of the ring. So I have my 6-membered ring, which looks something, look at this. I made a bond here. I've still got this bond here. I still have my methyl group, and there's my unpaired electron. And then we can see our next allylic radical is right here. So we're going to do another mechanism. Okay, so two fishhooks meeting, that forms the new pi bond, and then we're going to end up with a tertiary radical here. So we put our resonance arrow in again, draw our 6-membered ring like that. And we end up with a double bond here, 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 and we end up with a tertiary radical in the end. So we'll come back to D later on, but I want you to give D the old college try with, trying to draw the, where was I? Trying to draw the fish hook arrows, okay? Hopefully you can all recognize the allylic radical is right here, but I want you to give that a shot, and then we'll come back and take a look at that one again later on. All right, these ones are a little more challenging, but they're very important. So I'm going to put a star, not because there's a mechanism, but because I'd say this is really important. It's an easy question for any examination board to come up with. I mean, it's very little thought required, whether it's MCAT, DAT, ACS, Mr. Dion, whoever you're learning organic chemistry from. All the person has to do is come up with a molecule and say, which one is the weakest bond, okay? So the way I'm going to do this is I'll use the colors on my iPad. If I put a green hydrogen here, if I put a blue hydrogen here, if I put a red hydrogen here, then we'll do a black one, I don't know, here. And then, I don't know, could we get another color? We could do a purple right here. Hopefully you can tell the difference between the black and the purple. Anyhow, could anybody tell me which one of these is going to be the weakest carbon-hydrogen bond? And think about the kind of radical you're going to form. Anybody have an idea about this one? Yeah, thanks, Rubio. Awesome. Yeah, it's definitely the blue one, isn't it, right? Blue is going to be the weakest one. Hey, Rubio, can I ask you another question then? Since you nailed that one, you're absolutely right. I'll just put here weakest. Could you tell me which one would be the strongest? And I'll draw the radical just for the heck of it. Might be a tougher question. I don't know. Yeah, absolutely, you guys. It's the green one, right? That one's going to be the strongest because it's vinylic. Yeah, thanks. Yeah, I know it's not what it's asking, but yeah, that's good work. Absolutely. So why did Rubio say the blue one is the weakest? Because you end up with a radical. Not only is it tertiary, this is my blue pen. It's tertiary allylic. So that's really going to be a weak bond. Okay, not easily abstracted, but with relative ease, we'll say. So this one, let's try it again. I put a black proton here and a red proton here and a green proton here. I don't know, something like that. And then we'll put a blue proton there. Could anybody identify the weakest carbon-hydrogen bond there? Yeah, thanks, Hannah. It's the red one. Yeah, absolutely. So awesome. We'll put here weakest. Okay. What's the rationale? You end up with something that's tertiary allylic again. Draw my 6-membered ring. Which looks like this. Okay. Once you form that radical, it is tertiary and it's allylic. That's a double whammy. For this one here, this one's kind of interesting. I mean, if you put let's say a blue proton here, that's going to be a super strong bond because that's vinylic. But really, there's only one here, because there's no protons here. I mean, you're not going to abstract any of these protons on these methyl groups. But if you pulled this one off here, this one's going to be the weakest because you end up with something that's allylic. So if I just pencil in, there you go. So you end up with something that is, I'll just put here, allylic. And so that's going to be the weakest one. And then let's try the last one quickly. If I put a black proton here and a red proton here and a blue proton here. Does anybody have, this one's interesting. I think it's a good question. Anybody have an idea here? Would it be the black, the red, or the blue? Yeah, thanks, Isaac. Absolutely. It's the black one, right? Why? Because the blue one is allylic too, but the black one is tertiary allylic, and the blue one is primary allylic. So let's pencil that in here. We'll put weakest, and if you pull that off, you end up with something that looks like this. There you go. So we'll put here tertiary allylic. Awesome. There you go. So you can see again how the questions are easy to come up with. But they're good questions, all right? And you know what is an organic chemistry? What does she or he have to be able to do? That person has to be able to look at a molecule and say, well, I think this molecule is going to react in such and such a way. Anyhow, all right. Well, let's move on to section 10.2, which deals with patterns and radical mechanism. One thing I've learned teaching science students is, um, you know, one of the things that makes the world a great place is that we're all unique. You know, if everybody was the same, it wouldn't be very fun living here. I certainly wouldn't want to be married to myself. But, you know, one thing that I've noticed that science students tend to gravitate towards are patterns, right? I'm like that. And I think a lot of my students are like that. They say, show me the patterns, I will learn said patterns, and I will master the material, right? And so what's cool is that with radical mechanisms, there are some really good patterns. We don't have the nucleophilic attack, the proton transfer. We don't have that stuff, but they do follow patterns, okay? And like I told you a few slides ago, and I didn't remember that it was on this slide, but radicals don't undergo rearrangement, okay? They just don't. So don't even bother trying. Yes, this radical would totally undergo a rearrangement. There's no debate about that. You would get a methyl shift like this, and then you would end up with this guy here. Anyhow, so, but again, a radical is not going to rearrange. Okay, so there's rule number one. But radical mechanisms, unlike the ionic mechanisms, which had four patterns, the radical mechanisms have 6 key arrow pushing patterns. And before you get intimidated and go like, oh no, there's more of them and they're all squeezed into one chapter, hold the phone, okay? Just wait until you see the whole thing before you make any harsh judgments, okay? The first one is called a homolytic cleavage. So this is where you take something that is not a radical. So you see that's not a radical. Well, we could even write that in here. I'm being a little bit silly, but this is not a radical. Obviously, you know that. And then you end up with a radical, okay? So you end up with a radical or radicals. So that's homolytic cleavage. The next one is addition to a pi bond. So you see that a radical is being added to a pi bond, and you end up with a radical. So this one, you start with a radical, end with a radical. The next one is a hydrogen abstraction. Well, you can figure out what that means. It's when you remove a proton. Okay, it's not the same as a proton transfer, right? You're abstracting a proton using a radical. So the radical forms a bond with a hydrogen atom, and then you're left over with a radical. So you notice that here we have a radical, and here we have a radical, right? Halogen abstraction is similar to the hydrogen abstraction. It's where a radical abstracts a halogen from, you know, a halogen molecule, whether it's chlorine or bromine. And we'll talk about why it's not iodine or fluorine later on. And we got 2 more. The next one is an elimination. We get some good news. The elimination is actually the reverse of number 2. It's the reverse of reaction 2, right? Go back here. Addition to a pi bond. If you do the reaction in reverse, it's actually the elimination reaction. So that hopefully simplifies things a little bit, okay? So in this one, the alpha carbon is pushed towards the beta carbon to eliminate a radical. Anyhow, and the last one is a coupling. Well, I also have some good news there. It's the opposite of reaction number 1. Reaction number 1 was the homolytic cleavage. This is just the opposite, okay? 2 radicals come together. So you're starting with radicals, and you end up with not a radical. Okay, so what did we see? We saw that steps 1 and 6, or reactions 1 and 6, are just the reverse of each other. 2 and 5 are the reverse of each other. But I want to tell you right now, 3 and 4 are not the reverse of each other. The reverse of 3 is actually another hydrogen abstraction. You see that the R would be pulling this hydrogen off. And the reverse of halogen abstraction is also another halogen abstraction. So just keep that in mind. Homolytic cleavage, addition to a pi bond, those are the reverse of elimination and coupling. But hydrogen abstraction and halogen abstraction are not the reverse of each other. Okay, so it says here, group the relationships. So we have reaction number 1, we have reaction number 6, we have reaction 2, we have 5, and then this is reaction number 3, and this is reaction 3. Okay, so then 4 and 4 would just be the same thing. The reverse of a halogen abstraction is a halogen abstraction. Okay, but hopefully that helps to kind of put things in perspective a little bit. So now what we're going to do is we're going to get into even more detail on these mechanisms. And we're going to break all these reactions. So all 6 of these, we're going to put them together, or sorry, we're going to organize them in a different way. Okay, what we're going to do is we're going to put reaction 1 in a specific class. We're going to put reaction 6 in a specific class. And then we're going to put 2, 3, and 4, all of them in a class together. Now, let me explain to you why we can do this. Because reaction 1 is unique. It's the only reaction where you start it with something that isn't a radical and then you get a radical. Reaction 6 is also unique. It's the only reaction where you start with a radical and then end up with no radicals. What do reactions 2, 3, 4, and 5 all have in common? Well, you can't see reaction 5 on here. Maybe you can't. But what they all have in common is that you start with a radical and you end with a radical. Okay, that's what they all have in common. So how do we label these? Well, let me show you. Okay, we call them initiation. So that would be the first reaction. Termination, that would be the coupling one. And then propagation, that would be 2, 3, 4, and 5. Those are all counted as propagation steps. Okay, so initiation, propagation, termination. Initiation, propagation, termination. I promise you, you have to know these terms. So now what we're going to do, and I'm sure you all figured most of this stuff out already, we're just going to look at it in a little more detail for a couple more minutes, okay? So what was initiation? Initiation is starting out with something that is not a radical and then starting or ending up with something that is a radical. So how do you even get this to happen? If you're wondering, you know, how do I take a molecule and just get it to break apart, okay, and give me a pair of radicals? Well, we're going to talk about that in a little bit. But then when we talk about propagation, what do addition to a pi bond? What does hydrogen abstraction, halogen abstraction, elimination, what do they all have in common? I guess this isn't the order they had them in the book, but anyhow, they all have in common is that you start with a radical, so radical somewhere, and you end with a radical somewhere. Okay, so that's what propagation is. Oops. And then termination, you can probably figure that one out. It's when you have 2 radicals, so radicals, and then you end up with something that is not a radical. Okay, the coupling or the termination step is usually students' favorite step because I will literally accept any 2 radicals coming together. If the 2 radicals exist in the reaction mixture, you can show any 2 coming together, and that counts as a termination step. All right. Now, do you have to be able to draw some fishhook arrows for some radical processes? Absolutely, absolutely. So let's see if we can put some fishhook arrows together. And something that you noticed when we drew the allylic radical like this is that when you're making your fish hooks, so when they meet together, so let's say you want to make a bond here, which we're going to have to, what you do is you kind of put one at the halfway point and then you put the other one at the halfway point. So since they're meeting together, they're forming a bond. And then this one's going to end up over here. So you end up with, you know, something that looks like that. Okay, so those are your allylic radicals. So but what about forming a bond? Okay, what if we want to form a new bond that's not a pi bond? Because you see here, we're forming a new bond that's a sigma bond. So how do you draw that? Okay, because here we're starting it with a radical, and it's going to pull a proton off of the HBr, and then we're going to end up with a bromine radical in the end. So what the first thing we need to do is get rid of this, and we need to draw the Lewis structure of HBr like that. Okay, so the way you show the bond being formed is this. So pay close attention. You put one radical out in the air, and then the other radical or the other electron, you kind of bring it out in the air and say they're meeting like that, okay? And you can put them anywhere you want. I don't really care about that. You can put this one here and then say, well, this one's coming out like this. You can make them almost touch. And you say, that is the representation of the bond being formed, okay? Now, I agree the bond is way down here in the end, but that is the bond being formed. And so the bromine radical is just going to be formed like this, okay? So this one would be classified as a hydrogen abstraction because you're abstracting the hydrogen from the HBr molecule. This one would be addition to a pi bond. So this one is addition to pi bond. Anyhow, so we have our pi bond here, and we end up forming a sigma bond off of here. And so how are we going to draw that? Well, we're going to put one fishhook here, and then we're going to take the unpaired electron, and we're going to say we're making a bond between the bromine and this carbon. The other radical is going to end up here to make a tertiary radical. And there you go. Okay, now for my students who are listening to me right now, give me a thumbs up if you think you could draw these arrows with a little bit of practice. Okay, you will have to practice it. But you can kind of borrow some of your skills, I would say, from the arrows that we drew back in chapter 7, 8, and 9, and 6, I guess, and in chapter 2 to some extent. Chapter 3, man, they came up in every chapter. All right, there we go. So, okay, so now what we're going to do in section 10.3. So we've covered the first two sections. 10.1, Checkaroo. 10.2, Dunsky. Now we're getting into section 10.3, and I remember studying this because the textbook that I learned from was taught it in a similar manner. And I remember being confused by this and being like, why are we discussing this reaction? Okay, what is the simplest possible organic molecule in the universe? The answer is methane, right? CH4. There is no simpler organic compound in the universe. And so what are we talking about in this class, in this chapter? We're talking about radical reactions. So one of the simplest radical reactions you could have would be the chlorination of the simplest molecule. So that's why we study this very specific reaction. So this is just one reaction out of, basically infinite reactions that you could perform, okay? But we're taking methane, and we're just chlorinating it, or you could say you're halogenating it to make methyl chloride, right, using chlorine, and H nu represents, right, that's, if you remember, E is equal to H nu, Planck's constant times frequency. This just means light, okay? You get methyl chloride and you make some HCl. So this is just a very specific reaction that we're studying, but we use it as a case study to help us understand initiation, propagation, and termination, okay? But it's going to be the same three stages for any kind of radical mechanism. So what's our initiation? Well, you can see that if you just mix up some chlorine gas and some methane, you have no radical. So what do you have to do? You have to form a radical. So it turns out that the reason you use light, so this is usually an ultraviolet light, it doesn't have to be, but UV light, you shine it on the reaction mixture. And if you're wondering, are you telling me that you have your reaction mixture in a flask, Mr. Dion, and then you just shine a light on it? So this is, it looks like one of my eyeballs that I draw. Okay, you take a light bulb and you just shine it on there? Yeah, pretty much. That's not a very good light bulb. Why did I draw my light bulb like this? There we go. Now it looks like another flask. Anyhow, so here's your light bulb shining on your reaction mixture. Anyhow, so what we do when we shine our light on our chlorine is that it actually breaks the bond between the two chlorine atoms, and you end up with a pair of radicals. Now this only happens to a very small extent, okay? You only end up with a small number of these, small amount of chlorine radicals, but I'll show you in a few minutes why you only need a small amount of chlorine radicals. So the next steps are the propagation steps, okay? We have the hydrogen abstraction and then the halogen abstraction. So you form a little bit of chlorine radicals in the first step, right? You take your Cl2 and you end up with what? A pair of these chlorine radicals. You have one like this and one like that. Okay, so one of your chlorine radicals is going to see a methane molecule and it's going to pull a hydrogen off in a hydrogen abstraction, and you end up with your methyl radical right here. Okay, well now your methyl radical is hungry for something else to complete the octet of the carbon. So now, since there was only a small number of chlorine radicals, most of the chlorine is still intact, right? Most of the Cl2 is still there. And so when the methyl radical sees a chlorine molecule, it's going to pull one of the chlorines off in a halogen abstraction. And now you've got methyl chloride. So this is called methyl chloride. And you end up with a chlorine radical. Now hold the phone. Check this out. You notice that in the first step, you consumed a chlorine radical, but in the second step, you produced a chlorine radical. And so that's why you only need one or two chlorine radicals. You don't need to make a whole bunch of these, okay? You only need to break it apart once or twice, okay? And then this is going to keep reacting. So this is the definition of a chain reaction. It just perpetuates itself. Once you form a chlorine radical, it can react, sure, but then it forms a new chlorine radical. So it makes one for you once it reacts. So the last step is termination, and that occurs when any two radicals come together. So you saw that we had chlorine radicals and methyl radicals. You can show two chlorines coming together. You can show a methyl and a chlorine coming together. You can show two methyl radicals coming together. As long as the radicals are present in the reaction mixture, you put in them to get, you show them coming together, and that counts as a termination. In the textbook, it says you annihilate the radicals. Okay, it's kind of a funny way of saying it, but anyhow. Okay, so give me a thumbs up if you're with me on initiation, propagation, and termination. These three steps. Everybody with me on the at least the idea of initiation, then propagation, then termination. Okay, so now that we have that, I want to go back, and I know this is coming up in another slide, but I just like to, teach go back sometimes. And I bet you that some of you noticed this. Actually, I'm sure you all did. You're all very astute, okay? You might have noticed this, that if you add these two reactions together, did anybody notice that the chlorine radical cancels and the methyl radical cancels? If you tally those two up, what do you get? You get methane plus chlorine gives you methyl chloride, so CH3Cl plus HCl. Well, it turns out that that's the overall reaction that we looked at right here, okay? So the idea is this. I'll show you. It's on this slide right here. If you add the propagation steps together, you end up with the net reaction. So if you ever have a question in the homework or practice and it says write out the propagation steps, if you add them up together and you cancel everything out that's identical, so you see the chlorine radical here, chlorine radical there, methyl radical here, methyl radical here. If it's identical on opposite sides of the reaction arrows, it cancels out. And if you end up with the net reaction, you've done it correctly. If you don't, something went wrong along the way. But as I was telling you earlier on, propagation is actually a chain reaction. Why? Because we start with a methyl radical, but we produce one at the end. Okay, so you're not left hanging. You have one at the end, and it's ready to go, kind of thing. There we go. So that's the chlorination of methane. And again, it's a very specific reaction. But what do we know about chlorine? Okay, well, chlorine is electron withdrawing, but it can also donate electrons through resonance. And so it turns out that polychlorination is actually very difficult to prevent. Why? Because the methyl chloride is actually even more reactive towards radical halogenation. So then you go from methyl chloride to methylene chloride, CH2Cl2, right? So you go from CH3Cl to CH2Cl2. Then you go to chloroform, which is CHCl3. Then you end up with carbon tetrachloride, which is CCl4. So it just keeps going on and on and on. And so if you want the reaction to stop here, if you're like, I just want methyl chloride and I want the rest of the reactions to leave me alone, then in that case, what you would do is you would put in a huge excess of methane, because if you have way too much methane, then the chlorine radicals are more likely to just see a methane molecule than some other intermediate or something. All right, so that's chlorination of methane. Now, before we move into section 10, or move on to radical initiators and radical inhibitors, which I will cover with you before we take our next break, I want to take a look at this question here. Okay, there is some work involved here. It says, be able to draw mechanisms as in Skill Builder 10.4. So make sure you take the time to take a quick peek at Skill Builder 10.4. Just in case you're wondering, radicals, last chapter of new materials. This going to be would this be on an ACS exam or an MCAT or a DAT or something? Absolutely, they ask questions about radicals. And so this question here is just saying, draw the mechanism for the following reaction: the chlorination of chloroform to produce carbon tetrachloride. So let me pencil down what the reaction is, okay? It's saying, could you draw the mechanism of taking chloroform, which is CHCl3, add chlorine, okay? And I'll just put H and U for light, okay? And then we end up with CCl4 plus HCl. Like that. Could you draw the mechanism for this? So when we're talking about radical mechanisms, okay, we're not talking about nucleophilic attack, loss of leaving group, proton transfer, and all that stuff. What we're talking about is initiation, propagation, and termination. So initiation, propagation, and termination is what we need to draw here. So our initiation step, is going to be what? It's going to be the formation of a radical. So we're going to take our chlorine, okay, just our Cl2 molecule. We're going to hit it with light, H nu. It's going to break apart to give me 2 chlorine radicals. So I'm going to end up with, sometimes people leave the paired electrons out. They just write the radical like this. I don't know. I think it's better to put all the paired electrons. So there you go. So that's initiation. Now what's propagation? Propagation is going to involve 2 steps. It's going to involve hydrogen abstraction. So we put it here. Propagation involves hydrogen abstraction. And then it's going to involve halogen abstraction. Okay, those 2 steps. So for our propagation, let's start out with our hydrogen abstraction. So hydrogen abstraction is going to be first. So we have our chloroform molecules, so CHCl3. Okay, I'm not going to put the lone pairs in here just to make things a little bit easier on myself. So we have our chlorine radical plus our chloroform molecule. So hydrogen abstraction. What's going to happen? The halogen is, or sorry, the chlorine radical is going to form a bond with the hydrogen, and I'm going to be left over with my CCl3 radical. So I'm going to end up with carbon radical, 3 chlorines, and I'm going to end up with HCl. Okay, now in the halogen abstraction, so now I'm going to put X abstraction. What's going to happen is my CCl3 radical, okay, is going to abstract a halogen. Now remember, there's only a tiny bit of radical, so there's a lot of Cl2 around. So I'm going to form a bond between the carbon and the chlorine and form a chlorine radical. So now I've got my CCl4 plus my chlorine radical like that. Now, I'm going to erase this after I pencil it in, but if you tally up these 2 reactions, if you did it, okay, you notice that the chlorine radical cancels and that the CCl3 radical cancels. So you end up with chloroform plus chlorine gives you carbon tetrachloride plus HCl. You end up with this reaction here. So I'm going to delete all that because I don't want it littering the slide. But now we're going to do the termination step. And so termination, you can draw any 2 radicals on this page that you want to coming together. So I'll just draw the CCl3 radical plus a chlorine radical like this. And then I'm going to say they're going to come together. Right? This is what the Beatles were singing about in Abbey Road. Come together, your carbon radical and your chlorine radical. And we end up with carbon tetrachloride like that. And there you go. So there's the mechanism of initiation, propagation, and termination for the chlorination of chloroform. So remember, CHCl3, this is called chloroform. Chloroform, which is a liquid. Okay, chloroform is a liquid at room temperature. Something that you might see in other chemistry classes, we don't really talk about, is CHI3. This is called iodoform, and it turns out it's a yellow solid. Anyhow, all right, so before we take a break, I want to cover a couple more concepts with you from section 10.3. This whole idea of a radical initiator, starting it with a non-radical and then making a radical. I told you in the last question that if you take chlorine and you shine light on it, you end up with a radical. Well, the bond dissociation energy of Cl2 is 243 kilojoules per mole, which is pretty high. And so if you want to use heat to break it apart, you actually need several hundred degrees. So I think it's even greater than 200 degrees Celsius, which is really hot. Whereas if you use an organic peroxide, to break that apart, you only need something like around 80 degrees Celsius, so not nearly as hot. And so that's why we use HBr and ROR. It's because you can make a radical out of this because the bond dissociation energy is so low. Something that we don't discuss in gross and gory detail is an acyl peroxide. So, but acyl peroxides do make good initiators, something to make a radical from, because when you form the radical, it's resonance stabilized. It says which initiator above initiates, so which initiator above initiates reactions most easily? The answer would be an acyl peroxide. And the reason why is because the radical is resonance stabilized, okay? And you can see that manifest in the bond dissociation energy, which is lower than all of them. Anyhow, so we have radical initiators, but you know what's funny about setting up a radical reaction is if you start a reaction in a flask, okay, so you start some kind of reaction in your flask and you're trying to do a radical mechanism where you want a radical to be stirring around and react. Well, you can also have molecules in there that can consume the radical and just destroy it. And so you have to purify your solvents very carefully from oxygen, okay? Because it turns out that oxygen is a radical inhibitor. Now, I know you're all familiar with the O2 Lewis structure, which is this, okay? But if you remember, O2 is actually diamagnetic. Nope. That's better. Okay. Oxygen is diamagnetic. It's actually a diradical. And so if you have a radical in your reaction flask and it sees oxygen, it's going to come together. And so it's going to destroy your radical. So that's not good. So that means you have to purify your reaction and can't have any oxygen in there whatsoever. I mean, even a little bit of oxygen from the room. Another radical scavenger or radical inhibitor is hydroquinone. I don't think I did put the mechanism here, but hydroquinone, it actually is a very good radical inhibitor. And the reason why is because if it reacts with a radical like this here, like this here, you end up ripping and you're like, well, now you formed another radical. Sure, but it's much more stable because it's resonance stabilized. And if it reacts a second time, then you end up with this diradical, and then you can try drawing the mechanism from here to here, but you end up with benzoquinone, which is a stable molecule. You see it's fully conjugated. Anyhow, it's not aromatic, but it is fully conjugated. Anyhow, so those would be examples of radical inhibitors. So if you want to destroy radicals, you would either put oxygen in your mixture or hydroquinone, one or the other. But if you want your radical reaction to occur, then you would avoid molecules like these. So I remember when I was a graduate student, I did some radical chemistry, and I had to be very scrupulous about the way I removed the oxygen from my solvent so it wouldn't ruin, my entire reaction. There you go. So before we get into the thermodynamics, I think we should take another short break. But students will sometimes say, "Oh, here we go again, more delta G and delta H." Okay, I can't. General chemistry won't leave me alone. Well, before we take our break, I want to share something with you that might encourage you, which is, I know you all remember the formula, which is shown here in the brown box. Delta G is equal to delta H minus T delta S. And I know you all know that delta G is the ultimate deciding factor as to whether a reaction is going to occur or not. Yes, if delta G is negative, the or reaction happens. If delta G is positive, it doesn't. But if we look at the enthalpy term and then the entropy term, in a halogenation reaction, you're starting out with two molecules and you end up with two molecules. And so you can actually kind of ignore this term. And so we can actually say that our delta G for our reaction is pretty dang close to enthalpy. So I don't like to say it's simple because it's not, but I would say it simplifies things a little bit. So when we talk about, is a halogenation reaction going to be spontaneous? We don't even think about entropy. We just look at the enthalpy terms and just move on from there.